I'm going to have a look at Pythagoras's theorem, show you what it is, give you a couple of examples of how to use it, and explain why it works. So the first thing is Pythagoras, the ancient Greek mathematician. This is his theory. Notice the spelling of Pythagoras and the pronunciation, which is like that, pi, thag, or as. And it's got the apostrophe because it is belonging to him. It's Pythagoras's theorem, also called the Pythagorean theorem by some. Now, this theorem relates to right-angled triangles, and it only works for right-angled triangles. So before you start using it, make sure the triangle you're using it on is a right-angled triangle. This is a right-angled triangle shown here, and we know it's a right-angled triangle because it's got this 90 degrees corner and the little square symbol here showing that it is a right-angled triangle. So this is 90 degrees. The other two angles, this one up here and this one up here, are not 90 degrees. They have to be less than 90 degrees. That is the kind of triangle to which it applies. Now, the side opposite the right angle, which is this side pointed out here, is the longest side of the triangle, and this will always be the case. We'll never find that one of the sides which forms the right angle is longer than the side which is opposite. If you don't believe that, try sketching out some triangles. However long you make this line, or however short you make them, when you try and join the ends, you will be drawing a line which is longer than both of your other two lines. And mathematicians give the longest line, the one opposite the right angle, a special name, and that name is hypotenuse. There I've drawn in which line is the hypotenuse and the spelling of it. If you can't remember the spelling, do try at least to remember the name, hypotenuse, the longest side in a right-angled triangle. And the reason for drawing attention to that is that Pythagoras' theorem states that the square of the hypotenuse is equal to the sum of the squares of the other two sides. Now, that sounds a bit complex, so let's break it down. If we give each of the sides a letter, we'll call this one A, this one B, and this one C. So this relates to, or the letters relate to their lengths, but A, B, and C are just labels for the sides. And C is the hypotenuse. So what Pythagoras' theorem says, and this is the beginning, the middle, and the end of Pythagoras' theorem, this is all that you have to remember, is the length of A squared plus the length of B squared is equal to the length of C squared, where C, this one here on its own, is the hypotenuse, the longest side. So that is what Pythagoras' theorem states. And I'll give you an example, and then I'll come back and explain why we talk about the sum of the squares of the other two sides and so forth. Here's an example. We have A, B, and C. We know the lengths of A and B, and we need to find the length of C. First thing we do is check it's a right angle triangle. In this case, we have to accept that it is. And which is the longest side? According to the diagram, C is the longest side. That is the hypotenuse. So the formula tells us that A squared plus B squared equals C squared. A is 6 centimeters, so 6 squared plus B squared. B is 8 centimeters, so that's 8 squared equals C squared, which is what we're trying to find. 6 squared is 36. 8 squared is 64 equals C squared. 36 plus 64 is 100. So therefore, if we square root both sides, we find that C is equal to 10. And the units we're using is centimeters. So 10 centimeters. So we've been able to find the length of this longest side, the hypotenuse, with knowledge of the length of the other two sides. And that is one of the main uses of Pythagoras' theorem. It allows us to find the length of sides. We need to know two, and we can find the third. Here's another example. We've got, in this one, we want to find the length A. We don't know what A is, but we do know that B is 12 centimeters and C, the longest side, hypotenuse, is 20 centimeters. Once again, we apply Pythagoras' theorem in the formula, and that tells us that A squared, which we don't know what that is, that's what we're trying to find, plus B squared. Now we know B squared, that's 12 centimeters, so that's 12, and it was B squared, so there's the squared, is equal to C squared, and C is 20 centimeters. So that equals 20 squared. So A squared plus, now 12 squared is 144, 12 times 12. And that is 20 squared, and 20 times 20 is 400. Now what we need to do is to get A squared on its own, we take away 144 from the left side of the equal sign. That means we've got to take away 144 from the right side as well. So A squared is equal to 400 minus 144. And if we do that, we find A squared is equal to 256. What we now need to do is square root both sides. Square rooting the left side gives us just A. The square root of 256, and that happens to be 16 centimeters. So we found the length of A by using the relationship A squared plus B squared equals C squared. And that's another way that Pythagoras' theorem can be used. So it's really very easy to apply. I did say I'd explain what I said earlier about the way you speak about Pythagoras' theorem. So let's just cover that. The thing that I said was the square of the hypotenuse is equal to the sum of the squares of the other two sides. So in this formula, you can see all of that gobbledygook. The square of the hypotenuse, the hypotenuse in this triangle happens to be called C. So there's this C and it's squared. So the square of the hypotenuse here is equal to, and we've got the equal sign there, the sum, and sum implies addition, so we're adding the squares of the other two sides. Well, the other two sides are called A and B, and they're both squared. So A squared and B squared are the other two sides squared. Adding them together gives you the sum, and that's equal to the square of the hypotenuse. So just repeating that phrase, Pythagoras' theorem can be stated as the square of the hypotenuse is equal to the sum of the squares of the other two sides. A couple of final points on the Pythagoras theorem is that there is such a thing as Pythagorean triples. And these are three numbers, as in triple, three numbers, which form the sides of the triangle. And they are whole numbers. So many triangles exist without whole numbers, but some exist with three numbers. The best known case is undoubtedly the 3, 4, 5 triangle, and this forms a Pythagorean triple. The largest number obviously relates to the longest side, so what we expect is that 3 squared plus 4 squared equals 5 squared. Is that true? Well, let's check it out. 3 squared is 9, 4 squared is 16, and 5 squared is 25. So does 9 add 16 equal 25? And the answer is yes, it does. So that's correct, and 3, 4, 5 is therefore a Pythagorean triple. There are other Pythagorean triples which result in whole numbers, and some of these, I'm not going to demonstrate them, but they are 5, 12, 13. There's another one which is 8, 15, 17, another one which is 7, 24, 25, and so on. There are lots and lots of these, and you can look them up on the internet if you're interested, or have fun finding out your own ones. So that was the first of the additional 2 points, and it's useful to remember 3, 4, 5. They happen to be consecutive numbers as well, which makes them even easier to remember, as well as being able to work out the lengths of these sides, given 2 of them, and knowing it's a right angled triangle. If we know all 3 sides, or we have numbers for all 3 sides, we can work out if we have a right angled triangle. So, for example, let me give you the numbers. I'll make these up. 7, 9, and 13. If we make a triangle with these sides, do we get a right angled triangle? Well, obviously 13 is the longest side, and 13 squared is probably 169. Yeah, that's right, 169. So the question is, do 7 and 9 to the other two sides squared and summed equal 169? Well, 7 squared is 49, and 9 squared is 81, And if we add 49 and 81, we get 9 and 1 is 10, carry 1. 8 and 4 is 12, and 1 is 13. We get 130. And 130 does not equal 169. So that means this triangle, the 7, 9, 13 triangle, is not a right-angled triangle. If it was, the two sides would be equal. And this is a trick sometimes employed to find a right-angled triangle, or if you need a right angle.
Pythagoras' theorem can be used to create a perfect right angle using any of the Pythagorean triples, but in this demonstration I'm going to use a 3, 4, 5 triangle, and I've got some pieces of toy Meccano here, a 3, a 4 and a 5. If you count the holes on this, you'll see that there are 4 holes, and therefore you may be concerned that that's not actually 3, but in length, 3 units, but it is because the 4 holes have 3 gaps between them, and you can see that perhaps a bit more clearly here with my ruler, which shows that the first hole is on 0, and then we've got 1, 2, 3. These could be inches or centimetres, they're just whatever size the Meccano comes in. So that's the 3, this one is the 4, and the last one is the 5. And what we do is put these together in a 3, 4, 5 triangle, like that, which I'll quickly do now. So there is the triangle put together, and you'll see that it has this right angle here opposite the longest side, and we can confirm that is indeed a right angle with this square here, and as you can see it is a perfect right angle. So that's the 3, 4, 5 right angle triangle. Very easy to construct your own right angle, and this is a trick that can be used by builders if you want to lay out foundations for a building and you need it to be square. You can take pieces of string, measure 4, measure 3, and make sure that it measures 5 from these points, or use sticks or anything like that to give you a perfect right angle.